Okay, so we are still on unique reactions, now part 2. The last meeting we talked about the nucleophilic substitution SN2 reaction. So it's the bimolecular substitution, and the rate of reaction, of course, is dependent on two reactants, the leaving group and of course the nucleophile. And in this case, we'll continue with our lesson, and we'll be talking about the SN1 reaction. So consider, for example, the reaction of third butyl chloride and water to form the third butyl alcohols. The chlorine here is substituted with OH. So your substrate is our third butyl chloride, or leaving group is this chlorine, and of course your nucleophile is water. So again, as I mentioned before, even if you don't see any electron pairs on your reagents, so you always have to remember that for group 6, like oxygen, sulfur, they always have electron pairs here, the non-bonding electrons. Chlorine also here has a non-bonding electrons. And so for water, having the non-bonding electrons, this will give water to be considered as a nucleophile. And if you remember what the nucleophile is it is a reagent or a substance that is electron rich. So therefore, this will seek a positive center. So on the other reactant, you will notice this carbon here will become partially positive because it's attached to chlorine, which is an electronegative atom. So chlorine will draw electron to itself. Chlorine will bear partial negative charge, and carbon here will bear partial positive charge. So the nucleophile here, which is water, will seek this positive center chlorine, and here you will have your product OH, and then your OH substitute chlorine, and this is an example of an SN1 reaction. So in this kind of reaction, and even before, it's also a nucleophilic substitution, but there is a different mechanism that's being followed. And in this case, you'll notice that despite changing the pH of the solution, they found out that there is no significant change in the rate of reaction. Therefore, they concluded that for this kind of reaction, it is not dependent on the concentration of water, because changing the concentration of the hydroxide, of course, you know that water can have can dissociate to form hydronium and OH. Now, changing the hydronium concentration and hydroxide ion concentration in water does not alter the rate of the reaction. Therefore, they conclude that for this kind of reaction, the reaction is not dependent on water or the concentration of the hydroxide ion in solution. It's only dependent on this one reagent here, which is third butyl chloride. So this result suggests that neither water nor hydroxide are involved in the rate determining step of the reaction. Instead, the rate of substitution is dependent only on the concentration of this one reactant. And because of that, we will follow the rate of the reaction is directly proportional to the concentration of the third butyl chloride. In equation, you will have that rate equals to K, where K is the proportionality constant, or the constant for the rate of the reaction times the concentration of your reagent here. In this case, this is your substrate. Okay, and because in this kind of reaction, there's only one species that's being involved, only one type of molecule, and therefore we call this one as unimolecular kind of reaction, or its first order, and we call it an SN1 reaction, substitution of nucleophilic unimolecular. So I think the last time we already discussed this one. To consider, for example, you have a flask now with different bottleneck here, and you have the sun, for instance, and you notice that if the bottleneck here in the first glass sun is narrower as compared to the other two, despite the fact that these two would have a large bottleneck, it's the flow of the sun up to this bottom is dependent on this narrow opening. So in the same way, that's also what happens when we have a reaction. Even if when you have a reactant that would produce a product, and in the course of the reaction, we produce, for instance, different intermediate species, intermediate 1 or intermediate species 1, intermediate species 2. When you have the reaction from the reactant to the intermediate species 1, which is low, and then you have a reaction of intermediate species 1 to intermediate species 2, and then another forward reaction from intermediate species to the product. And this second and third step is fast. So even if they're fast, this kind of reaction, the first step, which is low, will determine the overall rate of the reaction. So therefore, the first step, the reaction from the original reactant to the intermediate species one will be what we call as the rate determinant step. So again, for the mechanism of the SN1 reaction, in the example of shown earlier, we have the third butyl chloride reacting with water to produce our third butyl alcohol, and of course your hydrogen chloride, or a strong acid will always dissociate itself into hydrogen ion and the chloride ion. The first step of the mechanism, I think I have mentioned this the last time. The first step of the mechanism, of course, is the leaving of the leaving group from the substrate. No? And when the leaving group leaves the substrate, we will always produce a carbocation. Carbocation is an organic species. It's an intermediate species that having a carbon that is positively charged. Okay, and this step is a slow step. And if you look at the free energy diagram, no, with its reaction coordinate from the reactant to the transition state, it's very slow, and there is a very large energy gap, free energy gap from the reactant. If you can see my arrow to this scanning peak here, and that is the production or the formation of your first transition state. So what is our first transition state? It is our carbocation. The transition state, first transition state is being produced is our carbocation. And to produce our carbocation from our primary reactants, here this one, it requires a lot of energy, and it's very, very slow. So you can only imagine that the reactant will have to climb or will have to overcome a large energy gap in order to produce this transition state one. And again, our transition state one is our carbocation. So the second step, once this kind of reaction produces the carbocation, so the carbocation will now react with our nucleophile. So the nucleophile, having electron pairs with it, will seek a positive center. In this case, it is the carbocation. So you will have a carbocation, and of course the nucleophile will use its lone pair to form a bond. So you notice here the lone pairs of water is only 2 pairs, no? And when it forms a bond, you will see one bond between carbon and oxygen, and of course maintaining bonds between oxygen and hydrogen plus another lone pair. And then you check on the formal charge of oxygen, having 3 bonds with the lone pair. Oxygen now will be positively charged. Okay, so this is now our second transition state. In the step 2, or the second step reaction mechanism, you will have the transition state product 1, carbocation, to your intermediate 2. Now you have this. It's very fast. There is only a very small difference in energy between this carbocation and your transition state 2 to produce your product here. Okay, your carbocation, this is your carbocation, and this is your product here, and this is the transition state. So I repeat, here is your reactant. Okay, there in the step 1 mechanism, this is your reactant, and this is your product here. You will have your product, but in order to form your product, this kind of reaction will have to climb a lot of energy. So the delta G is very, very large between this reactant and the transition state. So the transition state is in between this one, transition state 1 is between this and this one. And this is your temporary intermediate 1 product. So now we proceed. Once the nucleophile attacks the carbocation, then you have your product, this intermediate product 2 will now react with another nucleophile, to form your final products, another step. And this kind of reaction again is very, very fast. So where is that in the energy diagram? You have here this reactant, and this is your product. Kaning na peak, this is your second transition state, or third transition state rather. Transition state kaning sa taas. So the energy gap between the reactant, this one, and your transition state 2 is very, very small, and therefore it's very, very, therefore the reaction is very, very fast. Your reactant, this one, doesn't have to climb so much energy to form your product here. So what happens here? You have your nucleophile, the electron pair here will simply have to seek a positive center. In this case, the positive center is not your carbon here. There is already a very positive center, which is hydrogen. You know, hydrogen man, because your oxygen is positively charged, no? And oxygen is an electronegative atom. It tends, when there is a positive charge on the atoms, it will tend to disperse this positive charge by drawing the electrons from all the neighboring atoms. So this one will draw electrons from the bond, so yeah, oxygen and hydrogen, and therefore hydrogen will become partially positive. So it becomes exposed, this hydrogen here, which is, it will become very positive. So the lone pair will have to attract this one, and you will form your product, HOHH, and that this is your hydronium ion with a positive charge. And the lone pair between oxygen and hydrogen will be drawn towards your oxygen. Okay, so mabalik and lone pair here. And then your alcohol will now don't have a positive charge, but it will be on the hydronium ion. This is your H plus, or your hydronium ion, because it always reacts with water, surrounded with water. So this is our final product. And if you sum up this step 1, step 2, step 3, your overall reaction will be the formation of this alcohol, your hydronium ion, and your chloride and ion. Where is your chloride and ion form? It's in the step 1. And where is your alcohol and HCO plus form? It is in the last step. Okay, so the first, of course, in all the step mechanism, the reaction can be reversible, no? But going forward will always be slow, and forward. The second and the step reaction, step 2 and step 3, step mechanism, step reactions are always fast. So this small step reactions, what we call a step reaction, step reactions. Now, these are the mechanisms to obtain the overall reactions of your reactants to its products. Okay, so that is the mechanism. You all just have to remember the mechanism of the SN1 reaction is very different from that of the SN2 reaction. If you remember your SN2, the reaction between the nucleophile and the substrate is concerted. Now it's simultaneous. When your nucleophile attacks your substrate, the leaving group will also leave at the same time simultaneously, no? And it will attack from the backside. In this case, so we'll look at the carbocation in the SN1 reaction. However, what happens is the leaving group leaves first before the nucleophile attack. So that is the difference between the SN1 and the SN2 reaction. Again, the first step is a heterocleavage, no? The leaving group will leave the substrate. And the second step is the production of your third butyl oxonium ion, the one with this third butyl oxonium ion. The OH is bonded or protonated. We call it protonated alcohol, this one. Okay, and then the last step is the removal of the proton in your alcohol by the solvent itself or the nucleophile. Okay, so you will just, one of the observations also with the SN1, you will notice that in the energy diagram of the reaction coordinate, no, there are a lot of steps. You have a lot of peaks that you will see, no, because you will produce actually different intermediate products and different transition states. So in this case, you have three transition states, and you have 1, 2, 3, and then before you have the final product. So product 1, product 2, and then the final product here. Transition state 1, transition state 2, and transition state 3. I hope that my cursor, you can see my cursor. Okay, now let's focus on the carbocation. So how what is the property rather of a carbocation? So a carbocation, which is bonded to three different atoms. So in this case, let's see what is a carbocation. Here in our carbocation, it is bonded to CH3CH3. Okay, so it's CH3CH3 here. So carbon is bonded to okay, back to the lecture. Sorry for the interruption. No? So where am I? So let's go back to carbocation. Okay, so the carbocation here, you have the possibly charged carbon center that's bonded to three carbon atoms or three CH3 groups. So since it's only bonded to three CH3 groups, now it utilizes the sp2 hybrid orbitals. It's different if the carbon is bonded to four different group of atoms. It will always use the sp3 hybrid orbitals. But in this case, it uses the sp2 hybrid orbitals. So to assume the shape, which is trigonal planar, and since it utilizes only sp2, so two p orbitals to form sp2 hybrid orbitals, there is one unhybridized p orbital that is not formed to form the hybrid orbital. So one p orbital is unutilized, and this is where this orbital is vacant. No? So here the blue one is the p orbital. If it is C double bond C, no, bonded to three different group of atoms, this would have been utilized to form a pi bond. No, if this is in the CH2 for instance, so there is three how do you say three group of atoms bonded to your carbon, and the p orbitals is used to form a bond to form a pi bond. But in this case, we don't have a neighboring atom here, and this p orbital is vacant, so it just lay up and below the sp2 hybrid orbital. This is vacant, and since this is vacant, it's actually the one that is being seeked, or seeked by the nucleophile to donate its lone pair. This is the carbon atom in its p orbital, where it accepts the. You remember this one? The water will give, or the nucleophile rather, will give its electron, share its electron to the carbocation, and this will be accepted in this p unoccupied hybrid orbitals. Oh, unoccupied p orbitals, sorry. Okay, so this is the vacant p orbital, and this is how it shows. If this is bonded, but this one is H3, but it's bonded to hydrogen, so there is an sp2s, sp2s, sp2s. If it's carbon here, you will have sp2 from carbon and sp3 from carbon. And there is a sigma head-on overlap. You remember the sigma head-on overlap. And this is not illustrated here, the orbital, but if this is an sp2, sp2, sp2 bonded to the, if carbocation is bonded to hydrogen. So you have an s orbital from hydrogen, which is spherical, 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 and this is the head-on overlap, and you actually form a sigma bond. But your p orbital again is an hybridized and it's vacant. So, and because it's vacant, it can accept the electron pair from your noctile. And the relative stabilities of the carbocation actually to become more stable if it's 3°, meaning there are more R groups attached to your carbocation. So 3° carbocation is much more stable than 2° carbocation, than 1° carbocation, or when there's only hydrogen atoms bonded to your carbocation. So you have here RR, it's 2°, there's only one R group, there's 1°, if there's three R groups, it's 3° carbocation. And why is that? What is the reason that the carbocation being a 3° carbocation being the most stable one? And the answer with that is due to hyperconjugation. What is hyperconjugation? The hyperconjugation is it would involve the electron delocalization via partial orbital overlap from a field bonding orbital to an adjacent unfilled orbital. So you remember your P here. So this is our carbocation. We have an unhybridized p orbital, and it's vacant. So you have an adjacent we have an adjacent carbon, for instance. This is our R. Now an R, let's say CH3. This is an R. Okay. So your carbon here is sp3 hybridized. The carbon here utilizes the sp3 hybrid orbitals. So it's 109.5. So it's not really that parallel to your P, but somewhat closer to being parallel. No. Kung P orbital ni siya, there will be a direct sideways overlap. Remember, sideways overlap up and down, the up and below the plane, and will form the python. But in this case, there is a sideways overlap between the sp3 hybrid orbitals. What is the term we use? There is an overlap, partial. So the term is partial orbital overlap because it's not totally vertical. So there is a partial overlap between the sp3 hybrid orbitals and the p vacant orbitals. Okay, and that is what you call as hyperconjugation. Now that will only happen during lots of time. So with any tendencies. Okay, noted. So this will only happen, hyperconjugation will only happen when your carbocation is bonded to a carbon having like an sp3 carbon. Okay. Pag hydrogen siya, so there is no hyperconjugation. So hydrogen lang S man siya and sp3. Since circular or circle ang s orbital sa hydrogen, no, so dili siya maka partial orbital overlap. But if the adjacent carbon sa carbocation utilizes the sp3 hybrid orbitals, it's possible to have a partial orbital overlap, and that will be the basis for hyperconjugation. Imagine ba ninyo, everyone? Guys, I hope that you're able to imagine that one, because kung pp, sideways overlap lang, or the p orbital, murag another p orbital ng inani vacant, no? That's how your p orbital would occur. Pi bond would occur. There is a sideway overlap. Remember your pi. Okay, so that is your hyperconjugation. So in the case of carbocation, the unfilled orbital is the vacant p orbital, and the filled orbital is the CH or the C sigma bond of the carbon atoms adjacent to the p. This is the one here. Okay, and so here, this CH or CC, there's another C here, would disperse the positive charge that's being paired by the carbocation here through, saan niya pag-disperse na, because it will sideways overlap, partial sideways overlap with the vacant orbital. So ma-disperse ang charge. And that is one way of stabilizing the positive charge on your carbocation. This is hyperconjugation. conjugation. Another way nga ma-stabilize ang imong carbocation is through inductive effects. So, unsa man ang inductive effects? For example, if ang R naa siya electron donating groups, no? Ang R group usually can disperse this one by donating, murag i-induce niya if there is a large bulky group here, i-induce niya ang carbocation here. That's what we call as inductive effect. Now, inductive effects, there are two types of inductive effects. Inductive effects, we call it electron withdrawing inductive effects. So, for example, naatay carbon here nga na siya NO2. So, si NO2 na siya tendency to, because na siya oxygen, so si oxygen is electron withdrawing, so na siya tendency to withdraw the electrons paingon sa iya ha. So kung i-withdraw na niya paingon kang nitrogen NO2 ang electron density between the carbon and sa R here, mahitabo is mas mamore niyon siya positive si carbocation. Okay, so we don't want that to happen because it will just make your carbocation more destabilized. So what we want is an inductive effect nga makadonate og electron, or specifically we call it electron donating inductive effect. We should have groups here like alkyl groups, big groups that will induce the silingan nga carbocation sa iyang electron density. No, ma-share niya iyang electron density sa silingan ng carbocation, which is of course positive. No, so that's another way of, aside from hyperconjugation, the inductive effect. In particular, inductive effect, the electron donating inductive effect. Or another way is a resonance system. So, ano sa ng resonance system? Pag naatay silingan nga double bond na carbon here. We will explain that later, and I hope in one of the examples later we can show how would a neighboring carbon atom having a double bond to undergo resonance with a positive carbocation, of course. So there are three ways again to stabilize our positive carbocation. First is hyperconjugation. Second is inductive effects. So ako na lang i-note diri in particular unsa nang inductive effects. The inductive effects in particular is the electron donating inductive effects. So because effects, there is another one such as there is another electron inductive effect, which can actually mas makasamot na hinuon siya ka-destabilize. So when we say factors that would stabilize a carbocation, kadtong makadisperse bitaw makatabang siya o lessen sa positive charge sa carbon. Of course, kung positive man gud, the more ma-positive si carbon, dili siya mas stable. Okay, so there should be a mechanism within the sphere kang carbocation nga ma-minimize ang positive charge. So, unsa nga mga possibilities nga ma-minimize? First, again, is hyperconjugation. Nga nung ma-minimize man ang positive charge because there is a partial overlap with the adjacent carbon atom, or CH or CC, kung carbon ni siya. So, in particular, pag ang carbon diri is sp3 hybrid orbitals. No? Pag sp3, this is an example of an sp3, S niya P, dako nga P, P3. No? 75% is P for an sp3 hybrid orbital. So, dili siya perfectly vertical, just like kung another P, kung P na siya, but mura siya og close to being vertical, parallel aning p orbital, no? So because of that, pwede ma-share niya ang electron density niya sa iyang bond here paingon din niya through hyperconjugation ang tawag ana. Okay, again, another way is the electron donating inductive effect. I-induce lang ang electron density gikan sa mga R groups. Murabag, of course, the electrons are always moving i-induce lang niya yung electron density paingon sa carbon, no, para ma-disperse ang positive charge. And of course, the third way is resonance. So resonance can only happen when you see a conjugated system. So ito lang siyang i-include here. Resonance such as naakay in the presence of a double bond. Or presence of double bond. That's where you can easily find resonance structure. Okay, I hope it's clear with you. Now let's proceed to the SN1 mechanism. So in summary, again, the relative stability of carbocations is 3 degree, which is the most stable, then 2 degree, 1 degree metal. So here, if you have, for example, CH3 here, and you have partially positive carbon here, no, so si carbon here would tend to induce the positive center here by donating the electron density gikan sa ani paingon kang carbon. So that is what we call as inductive effect. So whenever you have large alkyl groups, it can actually donate electrons paingon kang carbon center, positive carbon center, by inducing, or we call it inductive effects. In particular, the electron donating inductive effects. Nganong ako nang i-emphasize? Because there is another kind of inductive effects, which is electron withdrawing. So we will discuss that when we, I think, go to the aromatics. No? Electron withdrawing is pabaliktad siya. Kung nakay group of atoms again nga diri sa picas, for example, an electronegative atom, no? An electronegative atom has the tendency to draw electrons paingon sa iyaha. So for example, na kay fluorine diri silingan kang carbon here. So if fluorine is the most electronegative atoms, mubira siya because it is an electronegative atom, it draws electrons to itself. So if this is a partially positive carbocation, no? So kung si fluorine mo draw electrons paingon sa iyaha, like you will notice an arrow paingon kang fluorine, like draws electrons paingon sa iyaha, madiplit na hinon og samot og electrons si carbon. So if madiplit siya samot og electrons, so it will make it more destabilized, and we don't want to happen. We only want groups that can stabilize, kanang makadonate og electron density paingon sa iyaha.